Tired of closure property yet? In week 4, we concluded our conversation about closure property by talking about closure on a set of rational numbers. We really only started talking about closure property to frame a conversation about the numbers and the operations together, and it was appropriate to conclude by talking about closure property on the set of rational numbers, because rational numbers are the numbers that students struggle with the most, particularly fractions. We'll begin by reminding ourselves what closure property is. So, for closure property, we say a set is closed if and only if, when you perform an operation on the numbers in the set, the result is also in the set. So, for the set of rational numbers, which is represented by the symbol Q, we say rational numbers are numbers that can be expressed as fractions, so fractions, decimal expansions that end or repeat, and when I say repeat, I mean have a pattern, the ratio of integers, and percent. So, our first example is the fourth, and we see that 1 over 4 is, some students think of it as $0.25, or 0.25, and that's 25%. We have 1/9, which is rational, 5/9, 25 over 5, negative 36 over 6, negative 4 over 3, and 1 over 3, which is a third, and a third as a decimal expansion is 0.333 repeating. A bar symbolizes that this number continues, and 33 1/3% is how we represent it as a percentage. The operations that we've been discussing are parentheses, exponents, multiplication, division, addition, and subtraction. But for the intents and purposes of closure on rationals, we only chose to discuss multiplication, division, addition, and subtraction. The essential question that we're asking ourselves for closure is what happens when I perform an operation on the numbers in the set, and whether or not the result is going to be in the set as well. So here we see that if we take a rational number and multiply it by a rational number, the result is rational. And we say that the set of rational numbers is closed under multiplication because the product of rational numbers is rational. Now, we did a concrete example and an abstract example, and we'll talk about the abstract example first. So, in this example, we took the fraction a over b, where a and b are any numbers, b being a non-zero number, so b not equal to 0, and c over d, again, d not being equal to 0, and multiplied them. To multiply these two fractions, we see that we multiply the numerators, a and c, and we get ac, and the denominators b and d, and we get bd. And in our concrete example, we see that 2 times 5 is 10, and 3 times 7 is 21, and that being a very procedural way to multiply fractions. Here we see, in another example, we have a third times 3, which is a third plus a third plus a third, and if we took this and put it here, this and put it here, this and put it here, we see we have 3/3, which is 1 whole. The next operation we discussed was division, and after several examples dividing rational numbers, specifically fractions, we concluded that the set of rational numbers was closed under division because the quotient of rational numbers is rational. If we move straight to the concrete examples, we see that 5 over 1, which is 5, divided by a half, 1 over 2, is equal to 10. Now, if we took 5 things and divided them into halves, we see that we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things. If we look at the case where we take 6 over 1, which is 6, and divide it by a third, 1 over 3, we end up getting 18, which is 1, 2, 3, 4, 5, 6. Each of those 6 things divided into 3 parts, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. An observation that students make is that if I multiply 5 and 2, I'll get 10, which is the numerator, and if they multiply 1 and 1, they'll get 1, which is the denominator. they multiply 6 and 3, they'll get 18, which is the numerator, and 1 and 1, they will get 1, which is the denominator. The process that they're describing is called a cross product. So here we see A over B divided by C over D results in AD, which is the product of the numerator of the first fraction and the denominator of the second one, and the denominator of the first fraction and the numerator of the second one in the denominator. To express this division a little differently, I can write it as a complex fraction, which is a fraction divided by another fraction. Here I see A over B on the top, divided by fraction bar C over D on the bottom, and now I can take this complex fraction and try to simplify it. So, if we observe, I multiplied the entire fraction by another fraction that was equivalent to 1. How I got this fraction was taking the denominator of this fraction and multiplying it by D over C. So if I take C over D, flip it over, and multiply it by D over C, I'm going to get 1, and these things are going to cancel out. If I do that on the top as well, I get a simple multiplication problem, and I can remember that when I have A over B multiplied by D over C, I get AD divided by BC. So essentially what was in the top stayed in the top, what was in the bottom stayed in the bottom, and I actually see that here I get AD, which is the same as multiplying the numerator of the first fraction by the denominator of the second fraction, and BC, which is the same as multiplying the denominator of the first fraction by the numerator of the second fraction. When we first began our conversation about closure, most students tried to conclude that all of the subsets of real numbers would be closed under addition. This was true. So the conclusion that students drew right away was that the set of rational numbers was closed under addition because the sum of rational numbers is rational. What was difficult for students was actually adding rational numbers, particularly fractions. So here we look at a concrete example. If we take 2/3 and add it to 4/5, the result is 22 over 15. Now, to put that into perspective for students, we use fraction bars. So we represent 2/3 as 2 shaded pieces of 3 total, and 4/5 as 4 shaded pieces of 5 total spaces. Now, a student who can already add fractions will probably say something like, if I multiply 2/3 by 5 over 5, I get a fraction over 15, which is 10 over 15. And if I multiply 4/5 by 3 over 3, I get 12 over 15. And when I add those two things, I get 22 over 15. But what's really happening here? If we look at this picture again, we can actually create equivalent fractions. So one of the things that does come out of this conversation is how to create equivalent fractions. Here I have 2 spaces out of 3. If I extended this, now I have 4 spaces out of 6, and 4 over 6 is equivalent to 2 over 3. Now I have 5 6 spaces, and 6 over 9 is equivalent to 2 over 3. Here I have 7 8 spaces, and 8 over 12 is equivalent to 2 over 3. Here I'm going to add 9 10 spaces, and 10 over 15 is equivalent to 2 over 3. So here I see 2 of 3, and I essentially took that 5 times to get 10 over 15. I can do the same thing with 4/5. So here, if I said 1, 2, 3, 4, so 5, 6, 7, 8, 8 over 10 is equivalent to 4/5. 9, 10, 11, 12 over 15 is equivalent to 4/5. And now that both of these pictures have 15 spaces, I can take 10 from here, and 12 from here, and the students would say that the total is this 15 over 15, which is 1, and then I have 1, 2, 3, 4, 5, 6, 7 over 15. So 1 and 7 over 15 is actually equivalent to a total of 22 spaces of 15 available spots. Subtraction is the last operation, and it's very similar to addition. Now, students are sometimes confused about whether the rational numbers are closed under subtraction, but they are, and after doing several examples, the students realize that the set of rational numbers is closed under subtraction because the difference of rational numbers will be rational. Now, we look at an example for this, and again we do the same thing that we did for addition. So we say 1/4 minus 1 over 16 is equal to 3 over 16. Now, the first thing the students are thinking is, can I represent this 1/4 so that instead of having 4 spaces, I have 16 spaces? And I can do that actually very easily. So here, I can take this and I can divide it into 16 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I see that 1/4 is actually equivalent to 4 over 16. And if I have 4 over 16, or 4 spaces of the 16, and I subtract 1 of those spaces, I'll get 1, 2, 3 spaces out of 16 spaces.